Hi, Stu Schwartz from MasterMathMentor.com. This is video AB16b. The topic is related rates, and this is the second half of the video. It covers the AB manual, pages 79 through 83. Follow this procedure to solve related rates problems. In AP Calculus, there will be a number of application problems. Look for words like increasing, decreasing, growing, shrinking, changing to identify it as a related rates problem. Make a sketch if it helps you visualize the problem situation. Be sure to label sides and angles with variables. Make a table of variables of given information and information of what you want to find. Make sure it matches the variables in your sketch. Pay attention to variables that are changing and those that are constant. For example, if you had a problem that talked about the distance from Houston to Dallas, that would be a constant. However, if you are traveling that distance and on the road, the distance that you are presently from Dallas is constantly changing. Choose an equation that ties your variables together. If it's a right triangle, then most likely it'll deal with the Pythagorean theorem, or possibly trig statements. If it's a circle, it might have something to do with area. If it is a cone, maybe it deals with volume. Next, look at your variable table and plug into your equation any variables that are constant. Do not plug in variables that are changing at this time. Now perform implicit differentiation to both sides of your equation with respect to t. Now plug in all variables from your table and solve for the unknown. Hopefully there will only be one unknown. If there is more than one, you need to use a secondary equation to find the values of other variables. Many times the secondary equation is the same as the primary equation. Finally, answer the question or questions that are asked using proper units. Remember that formulas with angles require radian form. Number 4 reads, an oil tanker leaks oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. How fast do the spill's circumference and area increase when the radius of the spill is, first, A, 20 feet, and B, 50 feet? This is certainly a related rates problem because it talks about a radius increasing. There is really no need for a sketch. We have a circle and it's already shown. We set up a table of variables. We know that r is first 20 and then 50 feet. And since the radius is increasing, dr dt is equal to 50 feet per minute. If we want to find how fast the spill's circumference is increasing, that is dc dt. And if we want to find how fast the area is increasing, that is dA dt. Our formula for the circumference of a circle is c equals 2 pi r. We now differentiate with respect to time and get dc dt equals 2 pi dr dt. And plugging in, we get dc dt is equal to 2 pi times 50 or 100 pi. Notice that dc dt does not depend upon r, so the circumference is increasing at 100 pi feet per minute at all times. The area of a circle is given by A equals pi r squared. We cannot plug in r because r is changing. Therefore, dA dt equals 2 pi r dr dt. So when r is equal to 20 feet, dA dt is equal to 2 pi times 20 times 50, or 2,000 pi square feet per minute. When the radius is 50 feet, then dA dt is equal to 2 pi times 50, or 5,000 pi square feet per minute. One of the most famous oil spills occurred in Prince William Sound, Alaska in 1989 when the Exxon Valdez struck a reef and spilled 11 million gallons of crude oil in the next few days. Oil spills have happened throughout history, but this one wasn't discovered for hours. And like the problem we just solved, the longer the time, the greater the radius, and the faster the area of the spill increases. Attempts to remedy a bad situation was made worse by bad weather and the remote location. Oil impacted 1,300 miles of shoreline, and the effect on wildlife was devastating. Many Alaskan beaches, some 30 years after the event, are still polluted with oil buried inches below the surface. There probably hasn't been a calculus class taught that has not seen a problem like number 5. A 13-foot ladder leans against a vertical wall. If the lower end of the ladder is pulled away at the rate of 2 feet per second, how fast is the top of the ladder coming down the wall at A, the instant the top is 12 feet above the ground, and B, 5 feet above the ground? Watch the short animation lower left, and if you have to, stop the video and watch it several times. Focus on the left-hand wall as the ladder comes down. Note that the speed increases even though the ladder is being pulled away from the wall at a constant rate. We now set up our table of variables in the order that the information was given. We're told that we have a 13-foot ladder, so z equals 13. The lower end of the ladder is being pulled away at the rate of 2 feet per second, and that is dx dt, which is a positive 2 feet because the distance from the wall is getting greater. We want to find out how fast the top of the ladder is coming down the wall, so we're interested in dy dt. Remember that y represents the distance from the ground to the top of the ladder. It is not the height of the wall. And finally, we're interested in doing this when the top is 12 feet above the ground, and that makes y 12. Later, we'll also do when y is equal to 5. The equation that ties everything together is x squared plus y squared equals z squared. Note that we can plug in the z because z is a constant. We cannot plug in x and y. So we get x squared plus y squared is equal to 169. We then take the derivative of both sides, and we get 2x dx dt plus 2y dy dt is equal to 0. We then take a look at what we're interested in. We want dy dt. We had better know everything else. Looking at the chart, we know dx dt, but we do not know x. So we have to stop for a second. So we could now go back to our equation, x squared plus y squared equals 169, and plug our value of y in and plug our value of z in, because we're trying to find x at that one particular time. And when And when y is 12, x turns out to be 5. So we now know everything but dy dt. So plugging in to our equation, we get 2 times 5 times 2 plus 2 times 12 dy dt is equal to 0, and therefore dy dt is equal to negative 5/6 feet per second. For part B, we can use our same equation, 2x dx dt plus 2y dy dt is equal to 0, but now we know that y is 5, and therefore we end up getting x squared plus 25 is equal to 169, and that gives x is equal to 12. So we go back to our equation and plug in, and we get 2 times 12 times 2 plus 2 times 5 dy dt is equal to 0, and now dy dt is equal to negative 24/5 feet per second. Notice that in both cases dy dt is negative because y is getting smaller. The top of the ladder is getting closer to the ground. Finally, the key to problems like this is organization. While there's no one set way to do it, I like to put the table on the left and then do the bulk of the work in the middle, and if I need a secondary equation, I like to do that on the right-hand side. Remember that somebody has to read your work. It has to be clear. 6 reads, a camera is mounted 3,000 feet from a rocket launching pad. The camera needs to swivel as the rocket is launched to keep it in focus. Part A, if the rocket is rising vertically at 800 feet per second, when it is 4,000 feet high, how fast is the camera to rocket distance changing? Part B asks, how fast is the camera's angle of elevation changing at that moment in time? The picture in this related rates problem is shown with the camera at the bottom right, and x representing the distance from the camera to the rocket, y representing the vertical distance of the rocket, and z representing the distance from the camera to the rocket. Theta, which will be used in a later part of the problem, represents the angle made with the ground and the rocket at any particular time. The table of variables is shown. X represents the distance from the camera to the launching pad, and that's 3,000 feet. Since the rocket is rising vertically at 800 feet per second, that's dy dt. And we are interested when y is equal to 4,000 feet. Two things are asked for: the camera to rocket distance and how fast that is changing, and that's dz dt. In part B, we are asked for how fast is the camera's angle of elevation changing, and that will be d theta dt. This again is a Pythagorean theorem problem. X squared plus y squared equals z squared. And since x is a constant, we can plug that in and get 3,000 squared plus y squared is equal to z squared. At this point, we take the derivative with respect to time of both sides, and we get 2y dy dt equals 2z dz dt. And if we divide by 2, we get y dy dt equals z dz dt. We are interested in finding dz dt, which means we better know everything else. We know y, we know dy dt, but we don't know z. So we switch over to our secondary equation to find z. We use the Pythagorean theorem again and get x squared plus y squared equals z squared. Now plugging in, we get 3,000 squared plus 4,000 squared equals z squared, and that makes z equal to 5,000. So now knowing z, we are cleared to plug in our information, and we get 4,000 times 800 equals 5,000 times dz dt, and therefore dz dt equals 4,000 times 800 over 5,000, and we get that that distance is changing at the rate of 640 feet per second. Remember, that is how fast the camera's to rocket distance is changing at the moment in time when the rocket is 4,000 feet high. Later, it will be changing at a different rate. In 6b, we're asked how fast is the camera's angle of elevation changing at that same moment in time. I include the picture and the variable table, adding in the fact that z is 5,000 feet. We are interested in d theta dt. When asked for d theta dt in a right triangle, to solve for it, we usually will use a trig function. And the easiest ones to use are sine theta, cosine theta, tangent theta. But it isn't clear which one we should use. Let's do all of them. Let's start with the sine function. Using these variables, sine theta equals y over z. Differentiating implicitly, we get cosine theta d theta dt equals, and now we have a quotient rule, square the bottom, z squared, and upstairs we get z dy dt minus y dz dt. We now plug everything in. Cosine theta we know is x over z, which will be 3/5 d theta dt, equals 5,000 times 800 minus 4,000 times dz dt. Now dz dt is not in our chart, but we calculated it just before. It was 640. If we hadn't done that work, we would have to then do it to figure out what dz dt is. So this is a lot of work. We also divide that by 5,000 squared. Now it's math. 3/5 d theta dt is equal to 36 over 625, and therefore d theta dt is equal to 12 over 125, and that will be measured in radians per second. Let's use the cosine function. Cosine theta is equal to x over z, and we can plug in the x, which is a constant, and we get 3,000 over z. So when we differentiate implicitly, our work is a little bit easier. Negative sine theta d theta dt is equal to, again, a quotient. We square the bottom, z squared, and upstairs we get 0 minus 3,000 dz dt. Again, though, to figure this out, we have to use the dz dt that we calculated before. If we didn't calculate it, we would have to calculate it. So we get negative 4/5 d theta dt equals negative 3,000 times 640 over 5,000 squared. And that turns out to be negative 4/5 d theta dt equals negative 48 over 625. And d theta dt is the same answer, 12 over 125 radians per second. Finally, let's use tangent. Tangent theta is y over x, which is y over 3,000. And doing the work now, we see that we get secant squared theta d theta dt is equal to 1/3000 dy dt. This appears to be a lot easier. The secant theta is 5/3, so secant squared theta is 25 over 9 d theta dt, and that will equal 1/3000 times 800. And doing the math, we get d theta dt equals 12 over 125, again, measured in radians per second. Does this mean that the tangent function is always best? And the answer is no. What is best is to use variables that you have information about. Originally, we were told information about x, y, and dy dt. Therefore, it is best to use any trig function with x and y, and in that case, we use tangent. Finally, so your answer makes more sense, you can change it to degrees. So we take 12 over 125 radians per second and multiply it by 180 degrees over pi radians, and that means that the angle of elevation is changing at 5.5 degrees per second. Number 7 reads, two cars are traveling along roads that meet at a 60-degree angle. Car A is 3 miles from the intersection, traveling at 40 miles an hour, while car B is 2 miles from the intersection, traveling at 50 miles an hour. How fast is the distance between the two cars changing if, first, they are both traveling away from the intersection, and second, car A is traveling away from the intersection, but car B is traveling towards it? Our picture is shown with sides A and B and theta between them. And we have side C, which represents the distance between the two cars. Next, the table of variables. We know that A is 3 miles and B is 2 miles. In both questions, car A is traveling away from the intersection, so dA dt is equal to 40 miles per hour. But in question 1, B is traveling away from the intersection, which means he's traveling at 50 miles an hour. But in question 2, car B is traveling towards the intersection, so dB dt is negative 50 miles per hour. We know that theta is equal to 60, and we're interested in dC dt. This is not a right triangle, so we cannot use the Pythagorean theorem. We use the law of cosines, which says that c squared is equal to a squared plus b squared minus 2ab cosine theta. But theta is 60 degrees, and that is a constant. So we get 2c squared equals a squared plus b squared minus 2ab cosine 60, but cosine of 60 degrees is 1/2. So we're left with c squared is equal to a squared plus b squared minus ab. And it's time for implicit differentiation. We get 2c dc dt equals 2a dA dt plus 2b dB dt minus a dB dt minus b dA dt. We take a look at all our variables and we know everything except c and what we're trying to find, dC dt. So we need to do some side work. We use the law of cosines again and get c squared is equal to a squared plus b squared minus ab, or c squared equals 9 plus 4 minus 6, and c equals the square root of 7. So we're ready to answer question 1. 2 square root of 7 dc dt equals 6 times 40 plus 4 times 50 minus 3 times 50 minus 2 times 40. And that gives dC dt equals 210 over 2 square root of 7, which is 39.686 miles per hour. So the two cars are separating by almost 40 miles per hour. In part 2, we use the fact that dB dt is negative because car B is traveling towards the intersection. So we get 2 square root of 7 dC dt equals 6 times 40 plus 4 times negative 50 minus 3 times negative 50 minus 2 times 40. dc dt is equal to 110 over 2 square root of 7, which is 20.788 miles per hour. So now the two cars are separating, but not by nearly as much. Number 8 reads, beach sand is poured, creating a cone whose radius is always equal to twice its height. If the sand is poured at the rate of 20 cubic inches per second, how fast is the height changing at the time the height is first 2 inches, second 6 inches? We draw our picture, and although it does not have to be to scale, I attempted to make it so that the radius is larger than the height. In our table of variables, we don't know the radius, but we do know that it's equal to twice the height. So we'll say that r is equal to 2h. 20 cubic inches per second is dv dt. And we know that h will equal 2 inches and then 6 inches. We are interested in both cases to find dh dt. The formula for the volume of a cone is V equals 1/3 pi r squared h. Now, we do not know what r is. However, we do know that r is equal to 2h and r is always equal to 2h. So it's a constant relationship, which means that wherever we see an r, we can replace it with 2h. So we get V equals 1/3 pi, quantity 2h squared times h, and that gives 4/3 pi h cubed. Therefore, dv dt is equal to 4 pi h squared dh dt. So for part 1, we plug in all our information. 20 is equal to 4 pi times 2 squared dh dt, and therefore dh dt is equal to 20 over 16 pi, or 5 over 4 pi, turning out to be 0.398 inches per second. And in part 2, we get 20 is equal to 4 pi times 6 squared dh dt. Therefore, dh dt is equal to 20 over 144 pi, reducing to 5 over 36 pi, which is 0.044 inches per second. Obviously, when the height of the cone is greater, the height is changing at a much smaller rate because sand falls off and creating a larger and larger radius. 9 is another cone problem. Water drains from a conical tank at the rate of 2 cubic meters per second. The tank is 16 meters high and its top radius is 4 meters. How fast does the water level fall when the water level is first 12 meters high, secondly 2 meters high? This is one of these problems that I alluded to early in the video, where a lot of information is being given to you and you have to put it all together. In the picture, we show the cone itself and then the water within it. The cone itself will use capital letters. So the cone has capital R as its radius and capital H as its height. The water level will have small r as its radius and small h as its height. Let's look at the table of variables. First, the fact that water is draining from the conical tank at 2 cubic meters per second is a measure of dv dt, and since it is draining, it is negative. The tank is 16 meters high, so capital H is 16, and its top radius is 4 meters, capital R is 4. We are interested in how fast the water level falls, so we want d small h dt. When the water level is first 12 meters high, so that's a measure of H. So we want first H of 12 and then 2 meters. So we have our formula for the volume of a cone, which is V equals 1/3 pi r squared H. Before we think about taking a derivative, though, realize that we have a product rule. And we will have an R and an H, and a dr dt, and a dh dt. And a number of those variables we do not have. So we'd like to try to simplify this down to one variable if we could. If you look at the picture, realize that we have two similar triangles with capital R and capital H and little r and little h. So small r is to small h as 4 is to 16. We then solve for one of the variables. Since we want dh dt, we would like to get rid of the r. So we'll solve for r, and r is equal to h over 4. Back to our v formula, and we get v is equal to 1/3 pi h over 4 quantity squared times h, which is equal to pi h cubed over 48. So differentiating, dv dt equals pi h squared over 16 dh dt. In question 1, h is 12, so we get negative 2 is equal to 144 pi over 16 dh dt. dh dt equals negative 2 over 9 pi, which is negative 0.771 meters per second. In question 2, h is 2, so we get negative 2 equals 4 pi over 16 dh dt. dh dt equals negative 8 over pi, or negative 2.546 meters per second. They are both negative because the water is falling. And finally, realize that when the height is 12 meters, the rate that the water level falls is very slow. But when the water level is only 2 meters high, it falls at a much faster rate because the radius is smaller, and therefore there is not nearly as much water in the tank. There are 30 problems in the homework section that test your ability to solve related rates problems. Some of them are easy, and some of them are a little bit more challenging. Spend some time on them because you can be guaranteed that a good related rates problem will be one of the major problems on the AP exam.